let's try to put together all the pieces of what we've been talking about thus far about the outer scale. Perhaps the best way to do that is with an example. So let's say you're at some location along a transmission line, and we'll call that location ZA. It's some number on your transmission line problem, some index that locates a position on the transmission line. Now, you don't know what that value is for some reason. You just know you're at some position. What is this value ZA? What you do know, for some reason, is that the reflection coefficient at that point has a value of 0.685 magnitude and a phase of minus 65 degrees for the reflection coefficient. Can we determine what the location on that transmission line is? Can we determine the value of ZA having knowledge of the reflection coefficient at that specific point, both the magnitude and the phase? Well, if we take the Smith chart and we can plot then this point on the Smith chart, it is on the complex gamma plane. We put a point which is distance 0.685 away from the origin, and likewise the point at a rotation angle of minus 65 degrees in this direction. If we were to draw a line from the origin through that point, it would intersect our outer scale at this location. Notice the reflection coefficient phase scale would have a value of minus 65, as it should, because the reflection coefficient phase is minus 65 degrees. But if we continue along that line, we find it also intersects the wavelengths toward load scale at a value of 1.6. In other words, a normalized distance of 0.16 lambda. And that actually should be, if it's y over lambda, that lambda should not be there. So 0.16 or 0.16 lambda in terms of the index. Can we conclude from that that the location on our transmission line, ZA, is 0.16 lambda? Well, the answer is no. And this is kind of the summary of everything we've got to at this point. This is the typical mistake that students make, that we can take the value of the reflection coefficient phase and use a Smith chart to determine the location where we are on the transmission line. Sure, from the outer scale, we get a value of this normalized index of 0.16, but that does not tell us the location of ZA on our transmission line. It's a different scale, and that's what I've been trying to point out. The mapping is the same. We cannot take this equation and from that determine the value of ZA. The reason is because we don't know how the index itself is defined with respect to the end of the transmission line, but more importantly, we don't know the load attached to the end of the transmission line, and therefore the load reflection coefficient. There is no way to go through and take this statement and from that determine ZA. From the Smith chart, sure, we can take the value and determine this index, but again, the important point of all this lecture is that this normalized index is much different than the normalized index of Z over lambda. So we're at some position on our transmission line, we'll call ZA, and we'll move a short distance along the transmission line from that point to a new location that we'll call ZB. So we're at ZA and then we move to ZB. At the location, that location on the transmission line, we find the reflection coefficient function. It'll have the same magnitude, of course, since the magnitude is independent of position of 0.685, but the phase of the reflection coefficient has changed to a value of plus 74 degrees. Now, if we look at the outer scale of the reflection coefficient angle on our Smith chart and locate 74 degrees, we notice that location corresponds to a electrical length scale, wavelengths toward load, on our Smith chart of 0.353 lambda. What is this value of 0.353 0.353 lambda tell us, or 0.353. Again, I should really have left the lambda off there since we've normalized it on this side. What does that tell us? Well, what it doesn't tell us is anything about the numerical value of ZB. Where are we on the transmission line when we have a reflection coefficient whose phase angle is plus 74 degrees? We can't tell from the Smith chart. This scale does not help us determine that. It does not mean that we are located at this location on our transmission line. All we know is that the value of plus 74 degrees corresponds to an outer scale value of 0.353 lambda. What does that value mean? Well, that value really, by itself, means nothing. From our Smith chart, we have determined from the reflection coefficient of our phase angle of our reflection coefficient, we've found that they've corresponded to two outer scale values of 0.16 lambda and 0.353 lambda. Again, both of those by themselves, either of them by themselves, mean nothing to us. What they tell us is, or how they're helpful, is if we take the distance between the two, if we take the difference between the two. Because if we take these two values and take their difference, we get delta y over lambda. But remember, delta y over lambda is the same thing as delta z over lambda. In other words, from these two values, we can, by taking the difference, we determine the electrical distance between those 2 points on the transmission line. I can't tell you what the index ZA is at that point on the transmission line, or the index ZB is at that different point on the transmission line, but from the Smith chart we can determine what is the distance between those 2 points. What is the distance in terms of electrical length, delta Z over lambda? So for example, in this example, excuse me, we take the difference between the two values on the outer scale and we get a result of 0.193 lambda. 0.193 lambda is the distance that we move from ZA to ZB. I don't know what the index of ZA or ZB are, and from most cases it doesn't really matter. What matters is how far we've moved in terms of wavelengths from one point to the other, and what we've moved in this case is 0.193 lambda. Let's try a different point on our transmission line. We'll call this point ZC. Again, this is some number, could be any number. And we find the reflection coefficient function, when evaluated at that point, has a phase of minus 112 degrees. If we look on our Smith chart, on the reflection coefficient phase at 112 degrees, all right, it'd be right about here, we find that corresponds to a electrical length value on our outer scale of the wavelengths toward the load of approximately 0.094. Again, I should not have put lambda here. It's just 0.094. If we go through then and determine the distance between our original point ZA, which had a value on the outer scale of 0.16 lambda, and ZC, which now again has a value of 0.094, if we take the difference between those two, we would get a negative 0.066 lambda. So what does the negative value mean? Well, this is just like the analogy of our mile markers. The sign, positive or negative, speaks to direction. If we took the direct difference between the location, the value that we got at ZC and ZA, and it turned out to be positive, that means that the location of ZC was further down the line, further toward the load, in the direction of increasing Z. But, as in this case, we take the difference and the result is negative, it means this location on the line, this location ZC, since the result is negative, the delta is negative, it means ZC is further up the line, away from the load, in the direction of decreasing Z. Negative means up the line, away from the load, the direction of decreasing Z, Positive means down the line toward the load in the direction of increasing z. Summarizing these results, and hopefully this is pretty obvious, not difficult to understand. In the first case where delta z was positive, that means that the location ZB was 0.094 lambda further down the line in the direction of increasing z, closer to the load than the initial value ZA. In the second example, where the delta was negative, that means our location ZC, the location ZC is further from the load in the direction of decreasing z, since the value was negative. It is a location that is 0.066 lambda back from the load on the transmission line. Make sure you understand the relationship between the positive value of delta z and the rotation of the phase angle around the Smith chart, around the complex gamma plane. This is something we've talked about before. As we move in the direction of increasing z toward the load at the end of our transmission line, the phase angle of the reflection coefficient will increase, and therefore we're moving in a counterclockwise direction around the complex gamma plane around the Smith chart. And that is shown by these examples we just did. When we had a delta z of a positive 0.193, we found that the phase angle increases by a value of 139 degrees. An increase in z as we move toward the load results in an increase in theta, a rotation around the Smith chart, which is counterclockwise. This is why the outer scale index, that electrical length that we've been talking about, wavelengths toward load, why it increases as we move counterclockwise around the Smith chart. We're moving toward the load, we're increasing the index z, and therefore the angle is increasing and we're moving counterclockwise. Conversely, if the delta z is negative, our index is decreasing. It's moving in the direction of decreasing z. It's moving away from the load. And as that value of z decreases, then the angle that we have, the phase angle, reflection coefficient, it likewise decreases. And we're moving then in a clockwise direction around the complex gamma plane and therefore around the Smith chart. A value of negative delta z corresponds to a rotation that is clockwise around that Smith chart. Again, from the standpoint of that outer scale of distance toward the load, as we move toward the load, we are rotating counterclockwise as we are moving away from the load, therefore, and we're going negative, reducing the value of index, rather, we are moving clockwise. Here is a graphical summary of what I just said. So we start at some location on the transmission line. We'll call it ZA, purple ZA. This is a number. And we know it has this reflection coefficient. The important thing from our purposes is the reflection coefficient angle of minus 65 degrees. And so it's a rotation here, 0. We're going to rotate down 65 degrees to minus 65 degrees right here. And of course that then is the reflection coefficient phase angle of this reflection coefficient gamma. If we look at the index there, we find that there is an electrical length for the outer scale, y over lambda, some value. Again, it doesn't really matter what value that is. But if we go through and add to that a value of 0.193 lambda, then we are increasing the value of the index. And because we're increasing the value of index, we're moving toward the load. We are rotating in a counterclockwise position. We stop here at whatever index results from an increase of 0.93 lambda. That location, we can draw a line through it there, and that will include the value of gamma, which is the reflection coefficient at our new location. We'll call it ZB. Again, the difference between the original location ZA and the new location ZB is that ZB is a distance delta Z of 0.193 lambda further down the line toward the load, and therefore increasing the reflection coefficient phase. If we go back and start the same location ZA, and now we move again along the transmission line, but in this case, move in a negative direction. In other words, move in the direction of decreasing Z, away from the load, toward the beginning in the input of a line. And let's say we move a distance of 0.66 lambda away from the load. In this case, since Z is decreasing, the reflection coefficient angle now is decreasing, and we move in a clockwise direction. We start at this mark for our outer scale. Again, doesn't really matter what that number is, but we subtract 0.066 from it, and when we get to that location, that is the new location, the new phase angle of the reflection coefficient at ZC. Doesn't matter what the index says for ZA, nor what the index says for ZC. What matters is the difference between those two is a minus 0.066 lambda, which means the distance between them, ZC, is 0.66 lambda further away from the load toward the beginning of the transmission line. If we look closer at the outer scale of our Smith chart, in addition to the scale which is wavelengths toward load, there's another scale just on the further away away from the unit circle, which is denoted as wavelengths toward generator. And if you look at that scale, it'll have the same characteristics. It'll start at 0 and it'll rotate all the way around the transmission line from 0 to 0.5. Halfway around, it'll be 0.25. So clearly this again is an electrical distance, a scale based on normalized length, some distance divided by lambda. The difference is the direction of increase. For the wavelengths toward load, it was increasing as we rotated in a counterclockwise direction. Now for wavelengths toward generator, we're finding that that scale will increase as we rotate in a clockwise direction, rather, around the Smith chart. Because of that, the alternative mapping that we can use for this scale, I'll again call it y. I probably should call it something else, or y prime or something, but it doesn't matter. Again, these mappings really, these equations are not very important. As we have seen, it doesn't matter what the value per se is of y at any point. It's the difference between them that is important there. But this is an alternative mapping to what we had originally, and we'll go ahead and put the math there. So this new scale, outer scale, wavelengths toward generator, again is an electrical distance. It rotates around the unit circle value from 0 to 0.5. It ends at the same location as the previous scale did. So what's the use? Why do we put this second scale on there, this wavelengths toward generator? Well, again, an analogy. If we're talking about I-70, we have our mile markers, which begin on the western edge of the state and increased as we move easterly toward Kansas City. But of course, we could have done this a different way. We could have had mile markers that started at 0 in Kansas City and increased as we move westerly across the state, ending at the Colorado border with a mile marker of 423. Of course, we could have done it either way. It's arbitrary. And the difference between these two mile markers, these two systems of mile markers, really are just their direction. One is associated with increasing, where mile markers are increasing in the direction as we move easterly, where the other set of mile markers, the values increase as we move westerly along I-70. What's the point of this second set of mile markers in this case? Does it really serve any purpose? Well, not really. This second set of mile markers, beginning Kansas City and increasing as we move westerly, would be completely redundant with the original set of mile markers. We could have one or we could have the other. It doesn't seem really necessary to have both. And it is true they are, in fact, redundant. The reason we might want to have two different kinds of mile markers, two different configurations, two different orientations, is because along I-70, of course, we have cars moving in two different directions. Some cars are motoring from west to east toward Kansas City, and in the opposite lane, or opposite lanes, cars are motoring east to west toward Colorado. So if we had these two different mile markers, certainly we would put the mile markers increasing as we move westerly in the eastbound lane. So the motorists would encounter a series of increasing mile markers. And this would, of course, make it easier to do the math in terms of how far you need to go to move forward. The distance between where you are and where you're going would always, or where you're going rather, and where you are would always be a positive number. And so the other orientation of our mile markers would, we're increasing as we're moving east to west, we put in, of course, in the westbound lanes for those motorists. Then as they drove along, they would see an increasing series of mile markers and would be able to hopefully more easily determine how far they needed to go to get to their destination. So again, we have two different orientations of our mile markers, two different definitions, each associated with the direction of travel, each associated such that traveling in one direction, the mile markers increase, or traveling in the opposite direction, the alternative index is oriented so those numbers increase as well. And this is the kind of, or the reason rather, we have the two electrical length outer scales on the Smith chart. We have one which is direction toward the load, and the other which is the direction toward the generator, the direction toward the source, the direction toward the input of a line. In other words, the direction away from the load. So with respect to transmission line, as we move toward the load, then we are, the index Z is increasing, and we are moving, of course, then in a counterclockwise direction. With this new index, where we increase value as we move toward the generator, in other words, away from the load, effectively what we're doing is reversing the direction of our index. The direction of increasing Z is really a direction that is moving away from the load toward the source. And so if we have problems where we start at one point and we move away from the load toward the source, we might want to use the outer scale, which is the direction toward generator, because as we move in that direction, we'll find the index is increasing. Now, this is completely redundant. We can use either one of them. The only reason that we'd want to use the direction toward the generator as we move, as we move toward the input of the line is the values increase, and therefore we are more likely to have problems that don't involve negative signs. And of course, that always can cause issues mathematically. You can use one or the other. Sometimes students are adept at switching between one or the other, whether they're moving from the input, the generator, toward input, the generator, toward the load, or switch it around if they move from the load back toward the generator. Other students will just use one scale and stick with it and either increase value with positive numbers or decrease locations or indexes with negative numbers. So one final issue with respect to Smith charts that can cause issues for students. And to use an example to illustrate this, let's say you are looking at a reflection coefficient which has a reflection coefficient phase angle of 170 degrees. And so we're basically rotating from the open circuit point almost all the way around the Smith chart, the complex gamma plane, to where the short circuit is. If we look at the corresponding electrical length scale on the Smith chart there, on the wavelengths toward load scale, we'd find that 100 plus 170 corresponds to a mile marker value of 0.486 lambda, or 0.486 0.486. So let's continue to move along the transmission line, up the transmission line to the load. And we're just going to move a short distance toward the load there. And when we stop on the Smith chart, we look and we find that the corresponding reflection coefficient phase angle would be a minus 144 degrees. Corresponding to that phase angle is an wavelengths toward load outer scale electrical length value of 0.05 lambda. The question then becomes, how far did we move up the transmission line toward the load? According to our analysis we've done to determine that, we simply take the mile marker, the location on the index where we stopped, 0.05 lambda, and subtract from it the location where we began of 0.48 lambda. But in this case, we do get a negative value. Now that shouldn't happen. We're moving toward the load using the distance toward load scale. And we should then get a increase of delta z, a positive delta z because of that. But this result mathematically shows that we get a negative value. In the example, this shows that we moved nearly a half wavelength away from the load, but what we really did was, of course, move a short distance toward the load. So why did we get this value, this large negative value in this case? Well, the problem here is that we moved past the problem point on the Smith chart outer scale. We have a circle, and so if we have any bounded scale, a beginning and the end, they must map onto each other at that point. And we have this instantaneous sort of change in our values. That's true for our reflection coefficient angle. We start at minus 180, and we rotate all around, and we come back to this point, and now we call it plus 180. So is it minus 180 or plus 180 at this angle here? Well, it's both of those values. We can call it either way. The same thing with our wavelengths toward load. We start at 0 at this location and we rotate around, increasing wavelengths toward load, 0.04, 0.06, all the way around where we come back the other direction, 0.48, 0.49, and then finally 0.5. Well, 0.5 is at the same location of 0. They come back onto each other. So which is it? Is it 0 or is it 5? This boundary that we have on the rotation causes all kinds of problems numerically if we're not very careful. Now, it's not hard to figure out, and it's pretty obvious how to deal with this situation. So to demonstrate the problem, we'll again use an analogy. And it's a simple one that you'll understand. And again, what I'm trying to show is that really the problem we're accounting here on our Smith chart is no different from this analogy, and just as simple to be able to fix, to be able to take care of. So let's say we have a situation where we look down I-70 toward the east, and at Columbia, Missouri. At Columbia, Missouri, the mile marker on I-70 is a value of 126. Of course, it's further east, so we should be able to take 126 and subtract the mile marker of Lawrence, Kansas from it, and that will tell us the distance from Lawrence to Columbia. When we do that, 126 minus the mile marker 388 for Lawrence, we get a value of minus 262 miles. Well, this would tell us, according to our interpretation of minus sign, that Columbia is 262 miles west of Lawrence, Kansas. I can assure you, and I've spent lots of times in both Columbia, Missouri and Lawrence, Kansas, Columbia, Missouri is not west of Lawrence. This numerical result occurred because we crossed the state line as we move from Lawrence, Kansas to Columbia, Missouri. When we cross the state line on the interstate system, the mile markers reset. And so as we cross the state line in Kansas City from Kansas, we get to the mile marker 423. All of a sudden, the mile markers, as we move into Missouri, reset to a value of 0. And then they increase to Columbia, where we see the mile marker is 126. Mile marker for the 126, or Columbia rather, is 126 miles east of the Missouri-Kansas state line. So how do we use our mile markers to determine the distance between Lawrence, Kansas and Columbia, Missouri? Hopefully it's hopefully it's obvious how to deal with this problem. We just break the problem into two steps. We first determine the distance between Lawrence, Kansas and the state line between Kansas and Missouri, and then we determine the distance from the state line to Columbia. And so it's relatively easy to do. The state line, the mile marker at the state line is 423 in Kansas, and we subtract from 423 the mile marker of Lawrence of 388, and we find 35 miles. The state line is 35 miles east of Lawrence. We travel 35 miles to get to the state line. The second, hopefully obvious step is to determine the distance between the state line and Columbia, Missouri. The mile marker at the state line in the Missouri side is mile marker 0. It's reset. And so we take the difference between 126, the mile marker of Columbia, and 0, the mile marker of the state line between Missouri and Kansas, and that gives us a value of 126 miles. Columbia is 126 miles east of the state line. And therefore, the total distance that we travel from Lawrence, Kansas to Columbia, Missouri is simply 35, the distance from Lawrence to the state line, plus 126, the distance from the state line to Columbia, Missouri, 161 miles in total. And of course, that hopefully is fairly obvious to you, and I didn't really need to explain how that might be done. So as simple as that solution was, we have an equally simple solution when it comes to dealing with this boundary problem, this state line problem in our outer scale of our Smith chart. We have a location, once again, where the electrical length has a transition. It starts at 0, it rotates all the way around, it gets back to 0.5, and then transitions again, resets to 0. And so when we cross that boundary, anytime you're rotating around your Smith chart and you cross this boundary here, back where the short circuit is, where the reflection coefficient phase on the outer scale goes from pi back to minus pi, or again the distance toward load transitions from 0.5 back to 0. If you cross that point, you have to stop and break your problem into two pieces. You want to travel to that boundary, to that state line, and determine your answer, and then likewise determine the second part from that boundary to where you're ending up as you move up and down the transmission line. So as we move down the transmission line toward the load, the index Z is increasing, and therefore we are rotating in a direction which is counterclockwise. Again, once we get to that boundary as our index in the direction wavelengths and direction of the load, as that index gets to 0.5, it transitions to 0, and therefore we need to break it into two steps. The rotation angle that we take, or the distance, electrical distance we take to get from our initial point to a value of 0.5, and then a second step where we take the electrical length, or determine the electrical length from that boundary to our final location. Add the two results together, step 1 and step 2, and we have our answer. So let's go back to our example. In our example, we have a reflection coefficient value at some location ZA on our transmission line, and we see the corresponding outer scale index, electrical length index, and that value is 0.486. We then move up the line a short distance, and we have a new reflection coefficient. And if we use the outer scale to denote the reflection coefficient angle, we find that outer scale value is a value of 0.048 lambda. So here it is, again, at a 0.486. And here it is at 0.048. And when we took the difference, we got this erroneous result. And of course, to really get the right answer, what we have to do is break the problem into two pieces. We start at 0.486, and we rotate around until we hit this boundary. And the difference between 0.5 and 0.486 is 0.14 lambda. That's how far we moved up the line to get to this location. At that point, we have to stop and write down that number. Now we have the second part of the problem. We've crossed the state line from Kansas into Missouri, metaphorically speaking, and so now we reset our outer scale at a value of 0. And we further increase toward the endpoint now at a value of 0.48 lambda. And what that means now is we've moved further down the line an additional distance of 0.48 lambda. That value there, by the way, is incorrect. That should be 0.48 lambda, the additional distance that we've rotated there. Well, we add the two values together, the 0.14 lambda we moved from here to this state line boundary, and then the distance that we move up the line from the boundary to our final location, and we see the total movement along that transmission line is 0.062 lambda. To move from this point ZA to this point ZB, we have moved a distance up the line toward the load of 0.062 lambda. All right. So that concludes the discussion about the outer scale, and there's a lot to it there. It took a long time, and it's because there's lots of issues that occur for students when they try to solve problems. There really isn't any sort of turn the crank algorithm to be able to use this outer scale to solve problems. You just need to figure out, make it make sense to you what this outer scale means, what it does, and how to use it. You really have to understand these values and make sense to you for any given problem that is presented to you.